Hi students, welcome back to another video session related to data structures. So this is the second BSc 4th semester computer science paper, unit 1. So this is Lakshman, lecturer in computer science from BR and GK Chalmers Degree College, Palkollu. Today I would like to discuss about the concept of sparse matrix in data structures. In the previous section, we are already discussed about the concept of data structure and what are the types of data structures, that is primitive and non-primitive data structures, and arrays concept were already discussed in the previous sessions. Now we have to discuss about the concept of sparse matrix in detail. So what is sparse matrix? So sparse matrix is a matrix represented in two-dimensional array with m columns and n rows. So it represents the n by n matrix. So there is a situation where the number of zero values than the non-zero values. That means, so this is the matrix. So here I am representing the values 0, 0, 0, 1. So how many zero values are there? In this row we have 3 zero values and only one non-zero value. So and the next row having 1, 0, 2, 0. So that means in this row the non-zero values are 2 and zero values are 2. Okay, so for example 0, 0, 0, 3. So in this row the values of zero values is 3 and non-zero values. In this matrix the total number of non-zero values is 4, but the zero values is 3, 5, 8. So the zero values is 8, non-zero values is only 4. So in this representation the amount of memory is wasted in this representation. That's why you are preferred the sparse matrix. Okay, so a situation in which the matrix contains more number of zero values than non-zero values, such matrix is known as the sparse matrix. So when a sparse matrix is represented with a two-dimensional array, we waste a lot of space to represent that matrix. So compulsorily it wastes the memory because it contains the lot of zero values than the non-zero values. For example, consider a matrix of size 100 into 100. So containing only 10 non-zero values. In this 10,000 amount of values, we have only 10 non-zero values. Remaining 9,990 values can having the zero values. In this matrix, only 10 spaces are filled with non-zero values and remaining spaces of the matrix are filled with 0. That means the total we allocated, how many bytes we have to allocate? 100 into 100 into 2, that is 20,000 bytes of space we are allocating. So and the accessing of 10 non-zero values we have to make scanning for 10,000 times. So the accessing, for if you access these elements, we have to scan all the elements of 10,000 times. So we have to avoid these problem in sparse matrix. We have to represent it in two types. One is triplet representation and next one is the linked representation. So sparse matrix representations are two types. One is triplet representation and linked representation. What is the triplet representation? So triplet, tree means 3, that means row, column and the value. So in this representation we consider only non-zero values. We does not consider the zero values here. Okay, we consider only the non-zero values along with their row and column index value. In this representation the zeroth row stores total rows, total columns and total non-zero values in the matrix. So let us consider the example. So of size 5 into 6 consists of 6 number of non-zero values. This matrix can be represented as shown below. Okay, let us take an example of 5 by 6 matrix. So this is the 5 by 6 matrix. So here we have 6 number of columns and 5 number of rows. So this is the 0th row, this is the first row, this is the second row, this is the third row, and this is the fourth row. And the columns, first 0th column, first column, second column, third and 4 and 5. So the matrix size is 5 by 6. So this is the 5 by 6 matrix. Okay, so 5 rows and 6 columns. So we are representing the values. So in this row, the how many non-zero values? We have only one non-zero value. In this row, we have only one non-zero value. In this row, we have only two non-zero values. In this row, it contains only one non-zero value. In this row, it contains only one non-zero value. That means we have to represent this sparse matrix in triplet representation. Triplet. So rows, columns, and values. We have to take rows, columns, and values. How many rows we have? 5 rows. How many columns we have? 6 columns. How many values? How many non-zero values? That means 1, 2, 3, 4, 5, and 6 non-zero values. So the number of rows, the number of columns, and number of non-zero values. Okay. So next, this is the 0th row. So in the first row, that means how many? First row means 0th row. 0th row contains the value 9. 0th row contains the value 9 in the column. In which column? 4th column. In which column? 4th column. The value contained. Okay. So in the second index, in the second row, that means in this matrix, the first row. So the first row contains the value 8. In the first row, the value contains 8. In the column, first column. In the column, first column. Okay. So in the third row, that means 2. So 2. So the non-zero value contains which location? 4. The 4. First one 4. Okay. In the location 0. And second row having one more non-zero value, that is 2. So 2 is the value in the second column. Okay. So third. So third means it is the third row having the value 5 at column 5. At column 5. So 4. So what is the value of non-zero value? 2. So column 4, the value is 2 in the column 2. So this representation is called triplet representation. This is called triplet. This is called triplet representation. I hope you have understood this triplet representation. So simply the 0th column contains the number of rows, number of columns, and the number of values, and all the remaining rows. This is the 0th row, first row, second row. So the second row contains two values. We have to represent it in 2 rows only. Okay, 2, 2. Okay, third row and fourth row. So in the second row we have two values. One is 2 and next one is the 4 and 2. Okay. So in the above example, matrix, there are 6 non-zero values. 9, 8, 4, 2, 5, 2, and the matrix is 5 by 6. We represent the matrix as shown in the image. Here the first row in the right side table is filled with 5, 6, which indicates that the sparse matrix of 5 rows, 6 columns, and 6 non-zero values. Okay. The second row is filled with 0, 4, and 9, which indicates the value of the matrix at 0th row, 4th column is 9. Okay. So in the same way, we are filled with all the remaining values. Okay, so this representation is known as the triplet representation. So another one is the linked representation. Okay, so this is the linked representation. So linked representation means we have to take 4 rows, that is So we have to take the 4 fields. One is row, column, value, and the next node. Okay, so this is the row value, this is the column value, this is the actual value, and the node value. So the node contains the address of the next node. Okay, so let us take an example. So this is the matrix. So 0 0 3 0 4 0 0 5 7 0 0 0 0 0 0 2 6 0 0. Okay, so here this is the one node. The node contains 4 parts. So the first part contains the row information, so 0th row. So this is the 0th row. Okay, and the column is 0 1 2. So which column? Second column. So the value is 3. Okay, so this is the node of which contains the address of the next node. For example, the address is 1001 here. For example, the address is 1001 here. 1001. So the 1001 is stored in this location because the next node address is this matrix. The next node address is stored in this location. Okay, so next, so 0th row, 4th column, the value is 4. In this location it shows the address of the another location. This is the another location, so this is the address. Okay, so it shows the address of the another location. So in this location it contains the address of the another node. So it stores the address of this location. So 312 is stores the address of another location. It stores the address. So the last node contains the null value. Here the last node contains the null value, that is row, column, value, address of the next node. So this is the row information, this is the column information, this is the actual value, and this is the address of the next node. Every node has an address. Every memory location has an address. The address is stored in the last field of the node. Okay, so this is the linked representation. So in sparse matrix there are 2 representations. One is triplet representation and another one is the linked representation. I hope you have understood this concept. So the next concept is linked list. So what is a linked list? So linked list is a linear data structure and is a very common data structure which consists of group of nodes in a sequence which is divided into 2 parts. So already you know, linked list is a linear data structure. It is a linear data structures like arrays. It is a very common data structure which contains the 2 parts. So the node contains 2 parts. So this is the node which contains 2 parts. One is the data part and next one is the address part. So every node has the data and its address. Every node has the data and its address. Okay, like that we are maintaining here. So each node consists of its own data and the address of the next node and form a chain. Okay, it forms a chain. Linked lists are used to create trees and graphs. Mainly linked lists are created to trees and the graphs. When we want to work with the unknown number of data values, that is infinite number of data values, we use the linked list data structure to organize that data. So with limited data we are using arrays. With unlimited data, unknown number of data values, we are using the linked list here. Okay, so linked list is a linear data structure that contains a sequence of elements such that each element links to its next element in the sequence. Each element is a linked list is called node. So what is the node here? This is the node here. So this is the node, so which contains 2 parts. One is the data part and next one is the address part. So the data and the address. So the address part contains the address of the next node. So this is the first node, this is the second node. The first node address contains the second node address. The first node address part contains the second node address. For example, this contains 100, this contains 1002. So what contains this? It contains the 1002. That means this is the next node address. For example, 1004 here. So this address field contains 1004. So what contains the last node? The last node always contains the null value, null pointer. Okay, null pointer is assigned. Okay, so this is the linked list. Okay, so what are the advantages of linked list? Linked list may have many advantages. Some of the important advantages are there. Okay, linked lists are dynamic data structure that they can grow or shrink during the execution of the program. So this is the dynamic data structure. That means we can add or remove the data at the runtime also. Okay, so we can add, we can grow or shrink during the execution of the program. You have to add and remove the data using the linked list. Linked list have efficient memory utilization. So memory utilization is very used in linked list. Here memory is not pre-allocated. Memory is allocated whenever it is required and it be deallocated. That means it can be removed when it is no longer needed. So whenever your data is no longer needed, we can remove automatically in linked list. Insertion and deletions are easier and efficient. If you are inserting the data, removing the data are very easy in linked list. Linked list provide flexible in inserting a data item at a specified position and a deletion of the item from the given position. We can add at any location, we can remove at specified location or any location. Many complex applications can easily be carried out with the linked list. Many complexity, that means difficult applications, can be easily maintained with the help of linked list. Okay, so it has some disadvantages also. The memory is wasted as pointers require extra memory for storage. We have to maintain huge amount of data. It requires a huge amount of memory. No element can be accessed randomly. It can be accessed each node sequentially, but because this is the sequential data structure. So reverse traversing is difficult in linked list. We have to traversing means we have to move from one location to another location is but reverse of the traversing is very difficult in linked list. Okay, so what are the applications of data structures? Okay, we are already discussed about the advantages and disadvantages. We have to discuss about applications of linked list. So linked lists are used to implement stacks, queues, graphs, trees, etc. Okay, you have to implement stacks. Stacks can be implemented using arrays or using linked list, and queues can also use arrays and linked list. Graphs, trees are also using arrays and linked list. So linked list can also be used to implement graphs. So adjacency list representation of graph you have to discuss later. So implementation hash table. So each bucket of the hash table can itself be linked list. Open chain hashing. So in hash table you have to use the linked list concept. Undo functionality in Photoshop or Word. So in Word there is a shortcut key that is Control plus Z, that is called undo operation. Okay, so undo application can be developed with the help of linked list one. So any polynomial can be represented in an array and in a linked list by simply storing the coefficient exponent of each term. So the intermediate results can be stored in linked list of polynomial can be represented in an array or in a linked list by simply storing the coefficient exponent of each term. So however, for any polynomial operation such as addition, multiplication of polynomials, linked list representation is easier to deal with these polynomial operations. Linked lists are useful for dynamic memory allocations. So if you are allocating the memory and deallocating the memory is very easily in the linked list. So in real life application where the circular linked list is used is our personal computers where multiple applications are running. So if your personal computers, the number of applications are processed, multiple applications are running, So in that situation, the linked list applications are used in that application. Okay, so all the running applications are kept in the circular queue list, and the OS gives the fixed time slot to all the running. The operating system keeps on iterating over the linked list until all the applications are completed. That means all the running application, the time slot is given by the operating system. Within the time slot, the process is completed by the operating system. In that, the all the applications, all the processes are maintained in the linked list manner. So one process is linked with the another process is linked with another. So this chain is happened in this running applications of the circular linked list. So I hope you are understanding this concept. Thank you.